Today we're going to talk a little more about logic, and we're going to do that by discussing something called sets. Very simply, a set is simply a collection of objects, and the element are those objects. So we could talk about the people in this room as a set. Everybody who's in Thurman 306 at 2 p.m. We're a set. And then each one of you individually would be an element of that set. We could talk about your textbooks that live in your book bag this semester. That could be a set. You could talk about your phones that are your songs that are downloaded to your phone. That would be a set, and each individual object would be an element. Each individual song would be an element to that set. There's a couple of ways to describe sets that we're going to talk about. There's more than this, but this is a couple of them. One is called a listing or the roster method. And we're going to just look at some numerical examples, although they apply to word examples or context examples too. But a listing or a roster method looks like what it says. You list it all out. So for example, if I was talking about the numbers that are bigger than 6, like whole numbers, I could do 7, 8, 9, and I could put my ... at the end, and this would be a way of listing those numbers. Okay? Now the next one, I'm going to write it down, and then I'm going to explain it, okay? So just write the notation, then we'll talk about what it actually says. This is called set builder notation. It starts out with that same fun curly brace that I just used. It's got an X and a vertical bar. Has that same X with a greater than or equal to symbol. And then some more notation that you might not have seen before. We've got another X. It looks like a script E, and it should look curvy like that. It's an actual symbol. Don't just think I'm writing any kind of E I want. It's a symbol that looks like, almost like a C with a line in through the middle of it, okay? And then I want you to put an N that's got 2 lines on the left. Where? After my, yeah, that's a 7. Yeah, that's just the number 7. Okay, so let me explain this description, and then we're going to actually write in several more basic set notation language symbols for us to know. So what this is actually saying is the X at the beginning is saying it's all the values. It's all X's. That vertical bar is the statement such that. Okay? The following conditions, the things that come after this vertical bar are what are true about the values. The first piece where it says X is greater than or equal to 7, you know what that means. You've seen and used greater than or equal to symbols before. All right? But the catch is that the way I listed it in the problem above, I didn't include, say, for example, 7.5. Right? So it's not all numbers. It's a specific type of numbers. And in particular, the way that I've described them is that it's natural numbers. So it's an N with 2 lines on the left. Now this symbol right here means is an element of. Okay, that's the notation I described above, element. It means it's one of these things. It's got these properties, an element of. So if we put that all together and we were to read that last statement, it would say X, such that X is greater than or equal to 7, and X is a natural number. Okay? Shorthand is all it really is. It's a shorthand way of describing it. So that was really nice. I gave you 2 symbols. One symbol I gave you looked like this. And I told you that it meant what? Is an element of. What do you suppose it means if I put this symbol? It's not an element of. You got it. Now, I mentioned this one on the previous screen as well, the N with the 2 lines on the left. These are natural numbers. Natural or counting, they're also sometimes called counting numbers. These are the numbers that you first learn when you start counting, which means they start with the number 1, right? So I'm going to put them in listing form to kind of give us an idea. This is 1, 2, 3, and so on. Those are natural numbers. And what we do in mathematics as children get older is we broaden the description of what a number is. The first thing kids learn to do is they learn to count, and they start with 1, 2, 3, 4, 5, 6. And if you stop them and you say, well, what about 1.5? They're going to look at you like you're from Mars, right? That doesn't make sense in their world. And in fact, that's actually quite a bit further down the line. The next thing that they actually learn after those counting numbers is the number 0, right? I have 3 oranges and you need 3 oranges, and I give you all of my oranges. How many oranges do I have left? Well, I need a number to represent that. I need a 0, right? So once I include the number 0, I have what are called whole numbers. It's a W with 2 lines on the left. Okay? So these are almost the same as natural numbers, but they include 0. Okay, I didn't really gain a lot of ground with that particular change, right? But conceptually, I actually did. And what you will see is that some of the numeration systems, some of the historical ways that people have done numbers have not included a number 0, and it creates all kinds of problems to not have a 0. So having a 0 is a big deal. The next thing that kids learn, maybe not the next thing, these next 2 things kind of happen at different points depending, but one of the things that kids learn is this idea of not having what they need. So for example, I have 5 apples, I need 7 apples. How many more apples do I need? Well, I need 2, and we would like a way to represent 2 that indicates that I don't have 2, but I need 2, so what do we need in order to do that? We need negatives, okay? So integers are what those are called. It's a Z with a line through the middle, like double lines in the middle of the Z. These are integers. And the reason it's a Z is because in Latin, the word integer starts with a Z. Okay, that's where that's coming from, just so you know. And so these are all the positive and the negative whole numbers. So we'll put a dot, dot, dot. I'll put -3, -2, -1, 0, 1, 2, 3. And so on. So we get the positive numbers and we get the negative numbers that coincide with them, or that are their inverses, is a word we've used before. Somewhere, usually even before talking about integers, kids do encounter the idea of having not all of something. For example, you have half of a cookie, right? That kind of a visual description makes a lot of sense to children, whereas the negatives kind of get confusing because we don't have a picture that's quite the same as a half of a cookie picture. And so those are actually called rational numbers. It's a Q with a line on the left. These are rational numbers. And to give you an idea of what these actually are, is these are numbers that can be written as a fraction. Now maybe they are. Maybe they are written as a fraction. It's 5/2, or it's 5/7. Okay, so maybe it's already in that form. That's great. Then that makes it a rational number. But it actually includes all the numbers that are on the screen here already as well. How could I write 2 in fractional form? 2/1, or even 4/2, right? Lots of ways I could write it and still be equal to the number 2. And then same thing with negatives, right? -4 would be -4/1, something like that. Decimals get included as well, right? Changing decimals into fractions. We don't do that in this particular course, but if you've had proportional and statistical reasoning, that's something we do in that course, right? Fractions to decimals and decimals to fractions. Also, it includes things like repeating decimals, because those actually can be written in fractional form as well. So you might be thinking, well, can't I just write all numbers in fractional form? And the answer is actually no, you can't. There are numbers that cannot be written in fractional form. Those numbers are called irrational. Some irrational numbers that you have seen before are pi, right? 3.141592, I don't know what comes next, but there's a whole bunch of, they don't ever repeat, they don't ever stop. It's approximately 3.14, it's approximately 22/7, but not exactly, okay? So the inability to write that as a proper, as a fraction, actual exact value fraction makes it irrational. There's some others you've seen, I'm sure, like square root of 2, right? It has a decimal representation, but you always have to stop the decimals because it never repeats itself. So irrational numbers look like a square root. Another type, a number, and this one you may or just may not have seen, is the number E. It usually comes up in like an Algebra 2 or Algebra 3 quantitative reasoning kind of course in high school. The number E, it's about 2.718. Again, it has the same an inability to terminate, just like pi does and like square root of 2 does. So rational numbers are written as a Q because when you think about them in a fractional form, right, like A over B, another name for a fraction or a division is a quotient, right? That's where the Q comes from. So we're not using R because Q stands for quotient. The other reason that we're not using R is because we already have the R representing something else. R is the real numbers. And real numbers include the rationals, the ones we just talked about, being able to be written as a fraction, and the irrationals, the ones that we can't. So maybe you stop there and you think, well, isn't that all there is? And again, the answer is no, it's not all there is. There are other types of numbers. The other types of numbers are called imaginary or complex. They involve square roots of negative numbers. Again, depending on your mathematical background, you may or may not have encountered this before. But there is something sort of outside of the image that we're creating here. But we're not dealing with that. We're stopping with real numbers. And to be honest, in this particular course, we're stopping with integers. We're not going to deal with fractions or decimals. Everybody's smiling, right? Okay, we'll deal with that proportional and statistical later on. But this course stops at integers. All right, so we're going to take a look going back into sets now. I just wanted you to mostly have some symbols so that when you see them used, you're not like, what are they using here? You've seen them, okay? Also, sometimes when they use these symbols, like let's say, for instance, this one, it doesn't look like a double line when in text, like if it's written in your book. It's going to look like a bold line on the left, and it'll look like regular script on the right. So it kind of looks like that, where it's just extra thick on the left, just so you know. That means the same thing. Okay, cool. So we're going to take an example. We're going to write it in both of those methods. Let me go back to that slide. The listing method, where we simply list it all out. The set builder notation, where we have this interesting symbols that are abbreviating things for us. And here is our example. It says the set of all natural numbers less than 5 and natural. Okay, so what is the first or smallest natural number less than 5? 1. And what else do I have? 2, 3, and 4. So this would be the roster or listing method for the numbers that are less than 5 and natural. Now, perhaps you're thinking, well, can't we just list them all? I mean, why do we need the funny notation? Well, I can list natural numbers, 1, 2, 3, 4. I mean, I can do that. I could even list them where I put the ... on the end like I did over here on this screen, right? All that's cool. But it only works because I have only whole values I'm writing. If I'm talking about those fractional ones, there's no way to write them out that way, right? Anytime I would write out, if I say, oh, I'm going to write it to the tenths, I'll use decimals. I'll write 1.1, 1.2, 1.3. I missed a whole bunch of numbers between 1.1 and 1.2. I can't always list it out. And that's actually the reason for the set builder notation, is because sometimes listing method just isn't possible. All right, so set builder notation, you start out with the same curly brace. Honestly, you can pick your favorite letter. I tend to just stick with X. And I write X such that. And there's two pieces that come next, and it really doesn't even matter what order they're in. But the two pieces have to do with how things are being described. Somehow I've got to talk about the fact that the numbers are natural, and then somehow I have to also talk about the fact that the numbers are less than 5. Those are the two mathematical statements that have to be written next to make sure that it's clear what I'm referring to. So I'll go with the order that we saw used over here, not because it matters, but because I'll just be consistent. So I'm going to list the part about it's less than 5. So this says x less than 5. Just like that. And then we put a comma. And then I somehow have to tell it that they're talking about natural numbers. So I say x is an element of, remember that's that curly E, and then I use my natural numbers symbol. That's set builder notation for the same thing. All right, so when we're talking about sets, there's different ways to compare sets. One way is whether the sets are equal. So equal sets are sets that contain exactly the same elements. Skip over one-to-one correspondence for a minute and just take a look real quickly at the next word. It says equivalent sets. I know it's on the next page of your book, but equal and equivalent we usually use interchangeably. Within set notation, they mean something different, okay? So equal does not mean equivalent. Now we need the definition in between to get to what they do mean differently. One-to-one correspondence. One-to-one correspondence is a pairing of elements between two sets such that each element of one set is paired with exactly one element of another. i.e., it means they have the same number of things. So equivalent sets are sets that have, for which there exists a one-to-one correspondence. That is, they have the same number of elements. So I usually give the example. It's not going to really work because I'm going to have to give some disclaimer to it in order to make it work. But for a long time now, my family's had 6 people. We've had 4 children and 2 adults. Of course, 2 of them are actually over 18, so maybe they don't even count as children anymore. I'm not really sure, but we're just going to say 6 people, right? So if my husband talks about his family and I talk about my family, those are equal sets because it's the same people we're talking about, right? Family living in our house, we'll say it that way. My husband has a brother, and his brother also has 4 children. So our family and his family, with those structures in place, have the same number of people. They don't have the same people. None of the people are the same, right? But we have the same number of people. So those would be equivalent sets because, for example, if we got together, everybody'd have one person to talk with, right? You talk to. There's a one-to-one way. So I can talk to the wife, and he can talk to the husband, and my daughter can talk to their daughter, and my son can talk to their son, and we can just pair it up all the way down, right? There's never a 3-way person where somebody's always getting their feelings hurt because they're getting left out. Okay? That's equivalent sets. So you might wonder if you did have, say, 6 people like our families do, and we did do this sort of getting together business, how many different ways could we pair off? I mean, because maybe, I don't want to talk to the wife. We've already talked about everything, but the husband and I both are runners, and so we want to talk about running. So we pair up for a little bit to talk, all right? How many different ways could these pairings exist? I need to be able to tutor their daughter in math, so we're going to be a pair at some point, okay? How many different pairings could exist? Well, here's the way that it works. So we're going to list this set. I'm going to just show you visually what it looks like, and then I'll show you how to calculate it. So there's one set over here with 6 elements. We're just going to do the numbers 1 through 6. And we're going to do the letters, the first 6 letters of the alphabet, A, B, C, D, E, F. So if you start thinking about how many different pairings there could be, well, I mean, the person 1 could pair up with A or B or C or D or E or F, right? Yeah. And we could do the same thing all the way down. But they can't pair up with the same person, so I have to be careful. So how do I calculate it? Because I can't just draw all the lines in. That doesn't work because, for example, this is giving me all the possibilities, but if person 1 is corresponding to person A, then number 2 can't go to A. That would create a threesome, right? We want to have the pairings going on. So what does it look like in terms of calculation? Well, it's easier to do, I think, if we make 6 spaces. So the first space represents person number 1. Person number 1 walks into the room and they've got to take a buddy to go have a conversation with, right? You could talk about this in terms of dance partners. There's 6 women in the room. There's 6 men in the hallway. Man number 1 walks in. He needs 1 dance partner. How many choices does he have? He has 6. But once he makes his selection and person number 2 walks in, he didn't have 6 choices. How many choices does he have? He only has 5 left. And the third person walks in and they only have 4. And then 3, 2, and 1. The last person doesn't really have a choice, right? There's 1 person left. Well, what do we do with all these numbers? Well, we actually multiply them together. So grab a calculator, if you will, and multiply 6 times 5 all the way down to 1. $720. There are 720 different one-to-one correspondences when you have 6 people or 6 elements in each group, in each set. That's a lot, isn't it? That's a lot. So when we're counting the objects in a group, and we talked about my family, you know, prior to what's going on currently with our family, we had 6 all the time, 6. That's actually called the cardinal number. So the cardinal number is simply the number of elements in a set. And the way that it is written is N, and it's a parenthesis S. There's not any multiplication going on. It's just notation. Number in the set. Okay? N of set S. Number of items in set S. If we can actually have, if we have a finite number, then it means that the cardinal number, the number it is a whole number. We can count it. So you start thinking about, you know, there's a passage in the Old Testament in Genesis where God tells Abraham to count the stars in the sky, right? And he's like, that's infinite. Well, it isn't, right? I mean, there's an actual finite number of them. It's just really big, so much so that you can't count. Okay, so we're not talking about just a really big number here. We're talking about something that absolutely cannot even possibly be counted. All right, that would be something that would be infinite. So an infinite is a number for which there is not a whole number that marks it. And then the last one that you should be aware of is the empty or the null set. So this is the set that contains no elements, has a cardinality of 0, and it has 2 ways to be written. One way is that you can write curly braces with nothing inside them. It's actually a very intuitive sort of way of writing it. It's not the most common way of writing it, though. The most common way of writing it is a 0 with a slash through it. So if you happen to be one of the people who like to write slashes through all your zeros, please don't. It has a different meaning for us. All right? It means the empty or the null set. It doesn't mean 0. It means set with nothing in it. So we're going to do some counting. We're going to count how many objects are in some sets. And we've actually done some counting already a little bit in class. Remember when we did Gauss's problem, we had to count how many were in our sequences? So you've had some practice with this counting idea already. We're just going to extend that to some different kinds of number sets. All right, so we're going to find the cardinal number for each of the following sets. And if you would, we're going to give these cardinal or these sets names. So I'm going to call it capital A rather than the little a, part A. This is set B, capital B. Set C is capital C, and then the D is capital D. Okay, it's just the name of the set. And the reason I'm going to do that is because what I want to do is I want to write down that the number of items in set A, right? This is the notation for that equals something. So how can I find out how many numbers there are between 9 and 99? How would you subtract? What numbers would you subtract, Alicia?
99 minus
Okay, so Alicia told me that last time, I think, too, where she liked to subtract the number at the beginning and then add one back in, like that. You did. And then I am more inclined to subtract the number that comes before, 99 minus 8, and we'll both get the same answer, won't we, Alicia? Yeah, we will. So what is 99 minus 9 plus 1? It's 91. Okay? So the reason that we don't want to subtract 9 and just stop there is because 9's in the set. And if you subtract 9, you're eliminating it from the set. So that's why adding 1 back in or subtracting 8 would be the idea. There's 99 elements. How about on B? How many are going to be in this set? What do you think? 1001? Yeah, it's 1001. How do we get that? Yeah, good job, Savannah. That 2002. Because that's where it ends, and it started at the original number. It's all the evens, right? And it's evens, not everything. So it's divided by 2. 2002 divided by 2, which gives me 1001. All right. A little bit with set notation on C. First of all, realize that the set itself is not to the numbers 1, 3, 5, 7, 9. That's not what it is, okay? The set is the square of all those numbers. So if I really wanted to figure out what numbers I have 1 squared, and 3 squared, and 5 squared, all the way up to 99 squared, right? This is my actual set. Think with me for a moment. Won't it still have the same number of objects that it would have had I not had squares? Yeah. The squaring changes the objects, but not how many of them there are, right? Doesn't matter that they're squared in terms of counting objects. So, how can it's equivalent to asking me how many are here as how many are here. Those two would actually be equivalent sets. Not equal, but they're equivalent. There's a 1-to-1 correspondence. I can pair up 1 with 1 squared and 3 with 3 squared and 5 with 5 squared and so on. How many numbers are there between 1 and 9, from 1 to 99? How many? There are 50. How do you know? Yeah, it's 100 divided by 2. It's the odd numbers up to 100, really, right? Yeah, it is. So odd numbers throw us in a way that even numbers don't. So let me help you, if you were dealing with odd numbers, to think about it a couple of different ways, and you can pick which one makes the most sense to you. When I think about this one, I think about doing it like this. So I take the 99 at the end, and I would subtract the number that's missing from before the 1. Whatever's at the beginning, whatever it is that would come in the sequence before that. So in this case, unfortunately, maybe it's a negative, but that's okay. What number comes before 1 in the pattern of this sequence? It'd be -1. Okay, most of the time it'll still be positive because the sequences don't start at 1. And then I'm dividing by 2 because I only have half of the terms, right? It's every other term. If I had multiples of 3, I would divide by 3. So what happens when I have 99 minus a -1? It's addition. So there's actually 100 divided by 2 to give me the 50. So that's one way to think about it. A second way to think about it is to think about what would happen if I had all of the numbers instead to 99. And actually, I could even have all the way up to 100. And then I said, I only need odds. Well, there's 100 numbers to start with. Odds would be half of them. It's another way to sort of think about it. It's maybe not as helpful if you didn't happen to start with 1 and go up, but it still works in this particular problem. How about D? D says, I need all the numbers x such that x is equal to x plus 1. On C, what I had us do first is kind of write out what some of those numbers would be, right? 1 squared, 3 squared, 5 squared, and so on. So what numbers satisfy this criteria? And they have to be natural numbers, it says too. Does 1 work? Let's try. Does 1 equal 1 plus 1? No, it doesn't work. How about 0? No. So what numbers work? There aren't any, right? There's no number that equals itself plus 1 more. It doesn't work like that, right? So how many numbers are in this description of a set? None. There are 0. The cardinal number of this set is 0. Now that means the set itself, D, is the empty set. Don't confuse those two things. It's the empty set because it has 0 elements. 0 elements in the empty set are two different things. Okay, I want to do a tiny little introduction with just the bottom of this page. We'll write down a few definitions and then we'll stop, okay? So what we're doing next in this section is we're going to shift gears a little bit to an organized way of sort of looking at and thinking about information. And that's actually called Venn diagrams. I do hope that you've seen Venn diagrams used. They are used clear down into like kindergarten. Well, they're used for different things sometimes, but they are used clear down into kindergarten. My daughter came home talking about them from 5th grade. My daughter came home talking about them in 2nd grade, using them for different things. So they are a way of illustrating ideas in logic. With Venn diagrams, a universal set is the set that contains all of the elements being considered. And complement means all of the elements not being described within the universal set. So let me just give you a very simple example. If we had the universal set that was all students at OBU, and the way that that would be drawn, in terms because these are pictures, is it's drawn as a rectangle, and it's labeled as U. So all of you, not me because I'm not a student, but all of you and all of your classmates are inside my rectangle, okay? It's kind of like, you know, what happens when we would all get together and, you know, have a chapel service if everybody were there, all the students. If we say that F is the female OBU students, the way that that's drawn is it's drawn as a circle inside of the rectangle, and it's labeled with the letter that you're referring to it as, in this case F for female. Then the way that you write complement, there's actually 3 ways to do it. The way that our book uses is a bar on the top of the letter. So what would be the description for the set of people who are students at OBU that are not in the category female students? It'd be male students, right? So that's what the description would be for this particular scenario. It would be male OBU students. And if you think about it in terms of my picture, where would that be located? On the outside. So this is F complement. So F complements everything I'm highlighting in yellow. I'm sorry, that's orange, not yellow, orange. F is everything I'm highlighting in blue, right? And the universal set is all of it. It includes everything. It includes everything. I'd like for you to know, just because it's good for you to be aware in case you were to use another resource somewhere along the way, a couple other ways that this can be written. One of the other ways it can be written is with a, looks kind of like an apostrophe. It's called an accent mark. Prime is what we usually call it, F prime. And sometimes you'll also see it written as a C, like a subscript or a superscript of C, like C for complement. So those are a couple of other notations. Our book is going to use the complement with the bar on the top, okay? All right, we'll pick up here next time.